Hello everyone. Today we're going to cover another topic of curvilinear motion, that is normal and tangential components. And today we're going to derive the velocity and acceleration equations for normal and tangential components. Deriving these equations will help better understand what is going on, and will be easier for us to solve the problems, including normal and tangential components. So see, we have an image here. So if we think these are the paths or road, and these particles are vehicle or object which is traveling along the path. So every second the particle is changing its direction, and each and every position the particle may have a tangential component, which is tangent to the path of the travel, and which could be at the velocity, and there's always a normal component at that position, and it could be for any particle and in any position. So we'll derive equation for this tangential and normal component. I found that most of you have a problem understanding how these equations came and derived. So we'll derive those equations today. So let's move to the next slide. So today's learning objective is derive the normal and tangential components of velocity and acceleration. And in the image you see an travel path of an airplane. So in every second is a curvilinear motion, and in every position it may have a tangential and normal components, and we'll determine this. Also another example of application is curved path here. So in every curved position it has a tangential and normal component, same as in frozen area. You have a tangential rectangular tangential and normal components. It is easier to use the normal and tangential components when you know the path of the particle. So let's see what we're talking about here. So N means normal and T means tangential coordinate system. We'll say it coordinate system. So for this we're gonna use and think about a path that we know. So it could be a known path. So if we know the path, for example, the path is y equals to a function of x. So you see in previous problem we said y equals to x squared plus something. So if it is a known path, then it is easier to describe in motion in instead of Cartesian coordinate. It is easier if we say it in a normal and tangential component. So the coordinate system of the normal and tangential component is variable, meaning it will change every time. So if my particle is right here, right now, so the origin of the normal and tangential component would be this point here, and the coordinate system will be like this. So one perpendicular and one tangential. So that will be the normal, and that's tangential. Now if my particle is currently here, after a certain time traveling a certain distance. Now my coordinate system, the origin will be here, and I will have I'll have the normal and tangent in this direction. So my t-axis, tangential axis, will be this, and normal axis will be in this direction, and this is always 90 degree. So we talked about it's a moving origin. Origin moves with the particle. So origin of the anti-coordinate system moves with the particle. And we know the path. We have to know the path. So in every position, if it's a curving path and you have a particle here, there is always a point. We call it where the center of curvature is. So we can call it origin double prime, and this could be the origin prime, which is the origin of the coordinate system, and the center of the curvature. So this is a curve, and this is the center of curvature, maybe the radius, and the distance from the particle to the center of curvature. So here to the curvature is rho. We can assume that is rho. So radius of curvature is rho. We assume, so which is the distance from here to here, rho. The origin, the start point, we can say that's an origin. We need this because we want to know what is the current position of the particle. So s distance from here to all the way up here, and radius of curvature. Now we're going to say center of curvature, which is we say O double prime, and we have defined the axis, tangential axis t and normal axis n. So on those axes we need to define a unit vector for the direction. So for normal n axis we define the unit vector as n, and for t axis we define the unit vector as t. So you see it's a vector forms, it's a direction on those axes. So if we know the position of my particle right here, which is s distance, and if we assume that a small displacement took place, so if I draw another position, which was the previous position of my particle, and this is the current position, so this tiny displacement, we can call it ds, a small displacement. So now let's define our velocity. So velocity, we know it is always tangent to the path, so which is the tangent in t direction. So let's define velocity. Velocity. So by definition, we know velocity, the magnitude of the velocity can be found as taking ds over dt, when d is the distance, any distance, for example from here to all the way up here, it could be the s, which is a function of time now, because every second is changing its position. So and we also know that velocity is always tangent to the path um, to the path. So if we want to know the tangential component of the velocity, then all you have to do is to take the magnitude of the velocity and multiply it by the unit vector in t direction. And we know that this is ds over dt. So this is this. So this is how we define the tangential component of the velocity. And we know there is no normal component of velocity because velocity is always tangent to the path of the direction it's traveling. Now let's discuss the acceleration. So acceleration so we know it is defined by derivative of velocity, and if we plug the value derived value that we derived in previous slide, so d over dt will be velocity magnitude and unit vector direction ut. So if we apply the chain rule, so we have to keep first we can take this one as derivative, keep this one as multiplied, and the next part we can take derivative of this, and while keeping this part intact. So derivative would be derivative of v multiplied by unit vector t, and then v derivative of unit vector t. So we can write that as a v naught ut plus v ut derivative, so we know this is the unit vector, this is the just derivative of velocity. We know this is the velocity. We don't know what would be the derivative of unit vector in tangential direction. So let's see how can we define that. Let's assume another known path of a particle, and if we say the origin center of curvature is that our particle is right here. So at that position, we will have a tangential component, and we assume that after a few seconds or time, when it traveled tiny displacement ds, we will have another component, tangential component, which is this. So if we assume that is ut, and we assume this one is u prime t, and again the radius of curvature remains the same because this distance is so small, ds, so even a tiny displacement, the curvature remains the same rho for both cases. And always the normal direction, which is in this direction, un, but we're not going to talk about that right now. So if we assume that d is very small, and this is the vectors, so we can have another And if we know that this displacement is delta ut, so we can say this dut is so this was ut, the previous position, and this is the final vector ut prime. So the final ut prime can be defined as the sum of ut vector plus the delta ut by definition. We also need to know another relationship, that is we know that arc of a circle is equal to that. I think we already know that radius, radius multiplied by the angle covered by that arc. So what it tells us that if this angle here is d theta, we can say that this arc, which is ds, can be written as ds rho, which is the radius of curvature, and then the angle d theta. This is one formula, and so we're gonna apply the same formula because this is the same angle. So if we have this angle, we know d theta, we can apply the same concept on this triangle. So here the radius of curvature is the ut, so we can write ut equals to dut, which is the arc here, and ut multiplied by d theta. Now we know this is the value, the magnitude of the unit vector t is 1, so we can write dut equals to d theta. In magnitude. So if we want to write it in a vector, keep it in the vector form, then we have to write that delta ut equals to ut plus d theta. So we can use both form, and this is the magnitude form, so no vector. If we take the magnitude, then this one becomes unity. Now I have a correction here. This one will be multiplication for multiplication because this is the same equation here. So our goal was to find the derivative ut. So if we take derivative with respect to time of this equation here, we get delta ut with respect to time dt equals to derivative of time, and we see ut d theta. So ut d theta, they are multiplied form. So again, if we apply the chain rule, we will get we have to do another conversion, since we have here that ut we know in previous drawing. So if our particle is here and here, this direction ut has has the same direction as our normal component, so which is here, would be same as parallel direction here. So this one, UN. So this direction, if we make that as this triangle, so this direction here and the normal component would be parallel. So the direction of DUT is same as the direction of UN. So we can replace that UT direction with U. We can write the delta UT as UN d theta instead of UT d theta, because the direction of the unit vector UN and delta UT is the same. So if we change that, we left with d dt UN d theta. And now if we take the chain rule, so we get dun dt d theta multiplied by plus d theta dt multiplied by un. So if we do that, we know that un is not in n direction, and with time the unit vector n doesn't change because that's the unit vector, so that becomes 0, constant. So we are left with d theta dt, which we can write theta dot and multiplied by unit vector n. So, and this is u dot t. So now we found that the ut derivative is equals to theta derivative multiplied by u. And so now in previous slide we also derived that ds equals to rho d theta. We're going to use that equation now, ds equals to rho d theta. If we take derivative of this with respect to time, we'll again apply the chain rule. So ds dt equals to dt rho d theta. So since rho is constant, one part will be 0. So again, applying the chain rule, we'll have s dot equals to this is not squared though. This is just tick mark. So just get rid of that. So we'll end up having d theta derivative multiplied by the rho, and the other part will be 0. So we don't have to worry about that. So from here we see, so this is another important relationship we'll use to derive the equation for the acceleration. So now if we plug this value here of d theta, we can say ut equals to s dot over rho multiplied by unit vector n. And we know that this is ds, this is ds over dt, so that is velocity. So ut equals to velocity over rho multiplied by unit vector n. So this is another important relationship. If we substitute these equations into our original acceleration equation that we wrote here, so we see derivative of velocity, which in t direction, so it will be acceleration component. This will be the normal component of the velocity, well, we have to put the value here. So let's rewrite this one on the next slide. So acceleration would be, we had this ut plus v ut dot, and if we define derivative v equals to tangential component of the acceleration, so that's that. And then for this relationship we just derived here, ut equals to rho over, okay, ut equals to v over rho un. If we plug that value here, we get v multiplied by v, v over rho un, so which becomes, this part remains the same, v square over rho un. So if we assume that v square over rho is the normal component of the acceleration an, so we can write acceleration is the summation of tangential component to the unit vector ut plus normal component n multiplied by unit vector un. So these are the vectors, these are not vectors. So the magnitude would be at square plus an square, and where an equals to v square over rho, at equals to v dot, which also can be written as at ds equals to v dv, which we kind of derived in our earlier lecture. So these are the things we have to remember when we apply tangential and normal component equations for anti-coordinates. So in next class we'll solve some problem on tangential and normal components of, and we'll see velocity and acceleration. Till then, thank you.